Right, cool. Now that we're recording, hello, people who have decided to join me. So right now we are going to cover equilibrium. Do y'all understand what equilibrium is?
Yeah.
Yes. Okay. So whenever you look at a reaction, say for instance, you have like H2 plus O2 becoming H2O. Now, for sake of example, we're going to pretend like this is a reversible formula. If it's a reversible formula, then equilibrium, I write it as EQ, or as the scientists write it, KEQ, is always going to be the point in which the forward is equal to the backward, right? It's where the forward reaction, KF, is equal to the reverse. Now, what does that mean? It means that when I have a reaction, the rates will change depending on certain factors, but usually if it's just the reactants at the beginning, they will try to reach this equilibrium point because they're trying to produce as much product as possible. And if it's reversible, like it is here, then the H2O is also going to try and separate itself back into H2 and O2 to the point where they reach equilibrium. So now that we understand that, do y'all understand what Kc stands for?
Concentration?
Kinda. Kc is your equilibrium constant. When looking at reactions, every single reaction has its own equilibrium constant. It's always going to be different based on the temperature, based on the pressure. It's completely unique based on what elements are being used. Just know that the equilibrium constant is something that all formulas have, though it is not always the same. So when looking at Kc, Kc can help you identify the concentration of your elements at a specific point, or in this case, equilibrium. Ta-da! So let me erase all this. So the easiest way to solve for Kc is to look at an example reaction. Now, Brooks should have done this in class, but just to show it, I will do it here as well. So say for instance, we have this reaction. All the lowercase letters represent the dang it, I'm forgetting my words. The coefficient, that's what it's called. The coefficient of the specific element, and all the capital letters represent the elements themselves. So for instance, this could be represented, rather than representing this as lowercase a capital A, I could represent this as 2 carbons. Now, when we solve for Kc, since we understand that it's the equilibrium constant, and I can use it to find the equilibrium concentrations of each of these elements, A, B, C, and D, I can set it up as a formula that looks like this. Oh, wait, hang on. Did it in the wrong order. My bad. Put your reactants on the bottom. There we go. So when I look at this, what does this mean? It means that, say for instance, I had that 3 carbon thing I had before, and it's being represented as lowercase a capital A. When I put it into my Kc formula, what it's instead going to look like is the concentration of carbon to the power of 3. I take this number and I turn it into an exponent. Does that make sense to everybody?
Yeah.
Okay, thank you. So why is this important? Well, if I have this and I know what the KC is, and I am given other amounts, or heck, I don't even need to be given specific amounts, but if I'm given certain amounts, I can solve for the equilibrium concentration. So let's take a look at question 1 of the review. We have a formula like 2SO3, which is a gas, which is in a reversible reaction to become 2SO2 plus O2. It's also a gas. Both of these are gases. Now, when doing equilibrium and concentrations, remember, we only care about gases here, right? And oh, wait, hang on, give me 1 second. So when we have this, we need to make a Rice table. What does that stand for? Well, R is for reaction. I is for the in between, or what is it? The initial amount, sorry. C is for change. E stands for equilibrium. Now, Rice tables aren't entirely accurate according to the scientific community, as I have found, but for this sake, we are going to use them because they can actually be used to help us find a theoretical yield a lot. What that means, if you do a lab with this, you'll figure it out. Now, in this initial problem, what we are given is this formula, and it says that, let me read out the problem here. First things first, what is the KC for the above reaction? Now, I've already made my Rice table, but something to note is, well, here's how you find the KC. To find the equilibrium concentration, I need to do what I did before. And remember, you always put the product concentration on top of the reactant concentration. And it doesn't, and you won't always have an equal amount of products and reactants. Sometimes you'll have 2 products, 1 reactant. Sometimes you'll have 2 reactant, 1 product. Just remember, that's how you do it. So in this case, my products would be oxygen. And there is no, what is it? Dang it, I just said it. I'm not going to put an exponent there because there's no number there. And then I also multiply that. We're not adding here, we are multiplying. The concentration of SO2 squared, because there's a 2 there, above the concentration of SO3 squared. Does that make sense as to how I got that?
Yeah.
Yes? Okay, good. If you have questions, please ask. This will get confusing really fast. So that's your answer to part A on that question. Part B, would Kp equal Kc? Now we'll get into Kp later. Just remember, just note that Brooks put no here, and she is correct. And she should be because she's the teacher. So let's go back to the Rice table. Now this is where we use the Rice table in part 3. The question says, if the above reaction starts with 0.25 molar, that's moles per liter, of SO3, what are the concentrations at equilibrium if the Kc equals 0.0000724? So let's begin with our initial amount, where the I is. For the initial amount, always assume that your products begin at 0. If your reactants are given to you, then you put your reactants, which is 0.25 molar here. Now we check change. Change is always done in X. Change is not done in an actual number, at least not for Rice tables. And X is always based on whatever number is here. So for my reactants, I'm always going to subtract For my products, I will always add. For my reactant, I see a 2 here, which means I will be subtracting 2x. If there was a 3 here instead of a 2, I would put 3x. If there was a 1, I would simply put x. Same thing on the product side. Have I confused anybody yet?
No.
Okay, good. So now that I've done that, I'm going to fill in my equilibrium side. Only here, I don't put numbers. What I am going to put is what is basically just I. Oh, I said I and I wrote a T. So you know you're tired. I'm basically doing I plus C here, right? I am doing 0.25 minus 2x. And it's okay if I leave it like that. This will come into play later as to what number exactly goes here. But for now, we're only going to put in what is basically a formula. And on the product side, I do the same thing. Only I'm not going to put 0 plus 2x because, oh wait, I put 2x there. That's only supposed to be x. Don't make the same mistake. So this is a completed rice table. Now, what can I do with this information? Remember that KC I wrote earlier? Well, if I know what the formula for KC is, and this question does give me the KC, I can figure out exactly what number goes in each of these spots rather than just the formula, because the formula alone is not entirely acceptable as an answer. So KC was the concentration of O2 times the concentration of SO2 squared times or divided by the concentration of SO3 squared. Now, if I know what each of those concentrations is represented based on X, then I can plug it in. Let's plug it in here. The concentration of O is simply X times the concentration of SO2, which is represented by 2x. And I'm going to square that. I'm going to divide it by 0.25 minus 2x. Does that make sense? Oh, and I'm going to square it. Does that make sense there? Okay, good.
Yeah.
So I set this equal to whatever the question has given me for KC. KC is 0.0000724. I'm going to write it in scientific notation, 7.24 times 10 to the negative 5. Here, what you need to do is solve for x. Now, I'm guessing most of you are online. So the easiest way to do this would be to plug it into Wolfram Alpha or into Mathway. But if you have a calculator, you can do this as well. Or you could simplify both sides, set them equal to 0 and solve for the quadratic formula, but that takes forever. Just know that in this case, x equals 0.0165. And actually, yeah, that's correct. So here, x equals 0.0165. Now that we know x, we can solve for every equilibrium value here. How do we do that? Fairly simple. Let me move all of this up a bit. Oh, there we go. So now that we know our equilibrium values, hang on, I am moving things on my screen that y'all can't see. Give me 1 second. So now that we know all of our equilibrium values, or now that we know all the numbers to get to our equilibrium value, I'm going to move all that off screen. So now that we have x, we are going to solve for the equilibrium concentration of each of our elements. So the equilibrium concentration, the equilibrium concentration for SO3 is going to be 0.25 minus 2 times X. That's going to equal, let me plug that in my calculator. Zero 0.217 molar. Remember, the units stay the same. Concentration for SO2 is going to be 2 times X, which is 0.0165. Zero 0.33. And for O2, it is simply X, which is 0.65. That's your final amounts. Is everybody clear on how I did all that?
But
Yeah.
how did you find X? Like, I know that you're supposed to plug in everything into the equation, but I don't know like how to like get X to the other side to equal 0.165.
Okay, so to make it easy, all right, this is technically cheating. All right, here's how I did it. Y'all can see my screen. Right?
Yeah, we can see it.
Yeah, we could see it.
Yeah.
Come on, my keyboard pop up. There we go. Dang it! This thing is not complying with me. Hang on. One second. This thing is not complying with me very easily. Go to Mathway. If you're on calculus, this is actually easier. You look at all your numbers. So I had it as, oh, wait a minute. No, sorry. So Brooks did it kind of wrong here. She put 0.25 as her final amount when I don't think it should have been this, but she and I can argue that tomorrow when I'm in her classroom.
Miss Brooks had said like comparing with the KC value, you could determine if basically X would equal to like nothing. So yeah.
Okay. I guess she and I can argue about that tomorrow. But so assuming that her version is correct, instead of doing 0.25 minus 2x, you would only put 0.25 on the bottom. So here I would put 0.25. On top, I would put x for oxygen, and then 2x squared for my what is it? SO2. Set it equal to my KC value, 1, 2, 3, 4, 7, 2, 5. Hit enter. Is it 725? No, it's 724. Hit enter, and then it'll give me x right here. Always in decimal form. Don't use it in an exact form. She's gonna be like, what the hell? But yeah,
Okay.
here's
see
how I
you
did it.
that then.
I got lazy and I didn't want to do all the math. But the other method is to get all of your x's on one side and then move this number to the other side as well. And it'll give you a quadratic formula. And then you solve for x either by factoring or by using the quadratic formula. And that's a pain in the butt because you have to do the whole negative b plus or minus the square root of b squared minus 4ac over 2a thing. But yeah, that's how I did on the math here. So just I used the computer program. Because, sometimes you just get lazy. Don't tell her I did that. I'm supposed to be teaching her class on my third rotation. So where's my pen? Here we go. So that's the answer to question 1. Is anybody confused as to anything I did?
Not yet.
Not yet. Okay, that's good. That's good. That's what we're looking for. we go back to the whiteboard. So now that we have all that cleared up, let me clear all of that. Let's go on to question. Oh, I actually skipped question 2 here because we can answer question 2 with other questions. So let's go to question 3. Now, we are talking about KC and QC. What is QC? Fairly simple. QC is the constant at any point. KC is the constant at equilibrium. So why does this matter? Well, sometimes you're given numbers and you don't know whether or not they are at equilibrium because the question doesn't tell you. In that case, you would consider those numbers at QC. So in this question, it is asking, and we're looking at question 3, we're skipping question 2. It is giving us KC, which is 0.020 at 445 degrees Celsius. It is asking us what will happen based on these amounts. We have the concentration of HI at 2.0. We have the concentration of H2 at 0.50, and we have the concentration of I2 at 0.10. And our formula looks like this. HI equals H2 plus I2. So first things first, let's set up our KC formula because we know how to do that. So if we put that formula into KC, I'm going to do my products over my reactants, and it is going to be concentration of H times the concentration of I over the concentration of HI squared. Now, why didn't I square H2 or I2? Because they don't have a coefficient there. That their coefficient is technically 1. So I don't need to put an exponent on there. However, I do need to put an exponent onto HI because there's a 2 in front of it. So now I have that. How do I find QC? Right? The big question is, how do I find QC in order to answer this question? Fairly simple. QC is the exact same formula. Write this out for y'all. Oh dear. QC follows the exact same formula. And if they already gave me KC, and they didn't tell me that these numbers that they've given me for the concentration of HI, H2, and I2 were in equilibrium, I can assume that these numbers are going to go into the QC formula. And with the QC formula, I can use that to not only find QC, but compare it to KC. So let's solve for QC. Solving for QC gives me the concentration of H2 is 0.50 times the concentration of I2, which is 0.10, divided by the concentration of HI squared. And plugging that into my calculator, 5.1 divided by squared gives me 0.0125. Now, what can I do with this information? I can compare it directly to KC. So let me free up some space here. Let's move this up there. So when looking at QC versus KC, which one is greater? That's the first question you always want to ask. Which is greater? Is KC greater than QC? Yes, because KC is 0.0200 if we're filling in all the zeros, and that is definitely higher than our QC value. So KC is definitely greater than QC. A good way to represent this visually is with a number line, where you start at 0 and you go to infinity. And you always put KC in the middle. Always put your KC in the middle. And your KC is at 0.02. Well, this is 1 less than 2 here. So we can assume that QC sits here at 0.0125. And you can do this on your test. It's probably a good way to visually see what's happening. So what does this mean? Well, remember, your reaction always wants to go towards equilibrium. If my reaction is going towards equilibrium, that means this QC will try to reach the KC value. It will move to the right. In the case of our formula, it will favor our products, right? Because at 0, there are only reactants. And at infinity, there's only products. At equilibrium, they are equal, which means at QC, there's some products, but there's more reactants. And if we're trying to get to it to equal, then it needs to favor products because it needs to make more products. And that's your answer. QC is less than KC, and it is favoring the production of products, which means it will make more H2 and I2. Is anybody confused as to everything I've covered for question 3?
Still good.
Yeah, I'm good.
What does QC stand for?
QC is just the constant at any point. There is no
So-
exact reason as to why they used Q as the label, but they just used Q as the label.
So the equation for QC will always be the same as the equation for KC?
Yes.
Okay.
Cool. Let's clear all this and head on to question 4. Heading on to question 4, consider the following reaction. Copper sulfide plus O2 creates a reaction like that. Initially begins with, a reaction mixture initially begins with 2.9 molar O2. Determine the equilibrium concentration of O2 if Kc for the reaction at this temperature is 1.5. So I know that. Actually, let me write out my formula here. So we have copper. I do it in orange. That's close enough to copper, right? Which is a solid. O2, which is a gas. In a reversible reaction with copper, which is a solid, plus SO2, which is a gas. Now, if you balance this equation, you will find that all the coefficients are 1, so I'm not going to write any of them in. And the next thing you need to do is, well, what else? What other information do we know? Let me select all this and move it over. Oh, come on. The whiteboard is not agreeing with me today. Move this over here. Well, what else do I know? I know that Kc is 1.5, and it is asking me for the equilibrium concentration of O2. So I'm looking for O2. Well, how am I going to find that equilibrium concentration? Simple. I need a formula and I need numbers to work with. So let's set up a rice table as we always do. I'm not going to write in rice. Y'all know where the numbers are. Now, the next thing we need to remember is when doing equilibrium, we only care about gases, which means I'm going to ignore all of this because it's a solid. And because if I put it all in, it's going to confuse the hell out of me. Any questions so far?
So if
No.
it's a solid, you don't do anything
Yes.
with it?
Yes, you completely ignore it. You can X out that section of the rice table. As for why, it's because solids and liquids always maintain a constant amount whenever you're doing a reaction like this. So that's why you never mess with solids and liquids when it comes to all your equilibrium stuff. Only care about gases because gases can change drastically.
Okay, thanks.
Now, my initial concentration of O2 was given to me. It is 2.9 molar. And because it's a product, I can assume SO2 begins at 0. Our coefficients are 1. So when looking at the change, my reactants are going to subtract, my products are going to add, and there's only one X to look at. So for O2, its equilibrium concentration is going to be 2.9 minus X, and for SO2, it is going to be X. Any confusion so far?
No, sir.
Okay, thank you. So now let's get into the next part. How do I find these numbers? Well, I was given Kc, and with the Kc formula, I can find X. So what is my Kc formula? Remember, we are ignoring solids. So I'm going to do my products over my reactants. My only product that I care about is SO2. And the only reactant I care about is O2. Very simple. I don't need to put in anything with the copper because those are solids. So now I plug in my information. I know that Kc is 1.5. I can set that equal to the concentration of SO2, which in our case is X, and the concentration of O2, which in our case is 2.9 minus X. Now I simply solve for X. Now this one I actually worked out properly. Multiply 1.5 times 2.9 and 1.5 times negative X. This will change to 4.35 minus 1.5x equals X. Add your X to both sides. Cancel out. Simple algebra. 4.35 equals 1.5x. Divide both sides by 1.5. X equals 1.7. Rounded to 2 sig figs here because I just did. Anybody confused on all that math?
No, it's pretty simple.
All right, so let me erase all the in between then, so that we can get to the main part. So remember, what I care about here is the concentration of the oxygen, because that's what the question is asking for. I know what X is, I can solve for the concentration of the oxygen. Fairly simple. I use this formula to solve for oxygen. The concentration of the oxygen at equilibrium is 2.9 minus X, which is 1.7. And that will give me, I wrote it down here somewhere, 1.2. And that is my final answer. Any questions?
No.
No? Good. Let's move on to question 5 then. On question 5, we now get into Kp. Calculating the Kp for the reaction. Oh boy. So in this reaction, we are looking at N2O4. That's not uranium, that's an O. It's an irreversible reaction with 2NO2. So the first question you're going to be asking is, well, what is Kp? Kp is the equilibrium pressure. K always represents something at equilibrium. P is always pressure. So Kp is your pressure at equilibrium. And this is going to change based on your constant. Now, let's take a look at the formula for Kp. Kp is equal to Kc, Kc times RT to the power of delta N. Kc is your equilibrium constant. R is another constant that is always going to be 0.0, hold on, 8206. And it's got a bunch of units at the end of it. It's basically just meant to cancel out so that your pressure is always in atmospheres. T represents, oh wait, here, let me start doing these in separate colors for you guys. T is your temperature, always in Kelvin. She'll usually give it to you in Kelvin, but if she gives it to you in Celsius, you need to convert it. And delta N, what is delta N? Delta N is the sum of the products, or sum of the coefficients of the products minus the sum of the coefficients of the reactants. Well, what does this mean? In our equation, we have two coefficients that we're paying attention to. There's a 2 on NO2 and a 1 on N2O4. To very, very simplify what I just said about some of the coefficients of the products minus some of the coefficients of the reactants, we're basically doing all the numbers in front of the products minus all the numbers in front of the reactants. So here it would just be 2 minus 1. So your delta N is 1. If, say, for instance, we had plus 3O2 here, instead it would be 2 plus 3, which is 5, minus 1, which equals 4. Does that make sense?
Yeah, it makes sense.
All right, cool. Let's keep going then. So let me erase all the in-between stuff now that we know it. So what else has this question given me? This question gives me Kc. And Kc here is equal to 5.9 times 10 to the negative 3. Very small number. It also gives me T, T, which is 298 Kelvin. I know that R equals 0.08206. And I know that delta N here is the sum of the coefficients of the products, which is 2, minus the sum of the coefficients of the reactants, which is 1, which gives me 1. So I'm going to use 1 here. The next thing I do is plug in all the numbers, which means that Kp equals 5.9 times 10 to the negative 3 times R, 0.08206 times the temperature, 298, risen to the power of 1. And that gives me a Kp of, plug it into your graphing calculator to figure it out, 0.14. If anybody wants to check that, they can. I may have accidentally plugged in a number wrong into my graphic calculator, but I'm pretty sure it is this.
Yeah, that's all right.
All right, cool, sweet. So another thing that you can look out for whenever you're doing this is you see all this stuff, right? All of this can be very simple depending on what the value of delta N is. Usually delta N will be 1 or 2, but sometimes it can be 0. So let's take a look at the next question. Take a look at question 6. Write the equilibrium constant for this expression. So PCl5, L3, liquid, plus Cl2, just a gas. That one's a gas too, right? Yes. So the first question this one asks is, would P be equal to the C? Justify your answer. Well, in order to figure that out, what you need to calculate first is delta N. And we know that delta N is the sum of the coefficients of the products minus the sum of the coefficients of the reactants. Only in this case, it's only going to be one of the products because PCl3 is a liquid, and we don't care about liquids. We only care about gases. So if we only care about gases, then what we're looking at is a coefficient of 1 minus a coefficient of 1, which gives us 0. And you remember in this formula, times RT to the power of delta N, we know that if 0 is where delta N is, then this entire section here, the R times the T, is going to equal 1, because anything to the power of 0 is 1. Does that make sense?
Yes, it does.
And if this section to the power of 0 equals 1, Kc times 1 is just Kc. Remember, anything times 1 is just itself. So if delta N equals 0, sorry if you can hear my relatives in the background. If delta N equals 0, Kp will always be equal to Kc. Does that make sense?
Yeah, it makes sense.
Yeah.
All right, sweet.
If it's a liquid, you don't count that at all. Like whenever you do the delta N, you would just
Yeah.
do the one. Okay.
Just completely ignore it. Just completely ignore it. Now that we are done with that, that's basically it for question 6. Let me check if there's anything else it asks. Nope. So whenever it says justify your answer, just say, since we don't include liquids, delta N is just 0. So now we go into question 7. In question 7, let us consider this reaction. NH4, HS, which is a solid, is in a reversible reaction with NH3, a gas, plus H2S, it's also a gas, at a temperature of 298 degrees Kelvin. This question, if I remember correctly, also gives us some concentrations. An equilibrium mixture of this reaction at a certain temperature has an NH3 concentration of 200.278 molar and an H2S concentration of 0.355 molar. What is the value of Kc at this temperature and what is the value of Kp? So here we're putting all of our collective knowledge together and we're trying to find Kc and Kp. So for this one, what we need is our other concentrations. So the concentration of NH3, which is 0.278 molar. The concentration of H2S, which is 0.355 molar. Next, as you always know, if we have stuff like this, let's make a rice table. And this is a solid, which means we could ignore it. Now, you might be asking, wait, why? It's our reactant. How are we going to just completely ignore it? Well, in this case, I did kind of lie. You don't need to make a rice table for this question because all the reactants are constant because they're a solid. All your product is already given to you in the form of these numbers. So those numbers are all you really need to care about. So no need to write all this in. So now we can just skip straight to the KC step. What is KC? KC would usually be our products over our reactants. But we've already said our reactant is a solid, so it doesn't matter. So we're just going to do our products. We don't need to divide it by anything. So in this case, it is going to be the concentration of NH3 times the concentration of H2S. Does all of that make sense?
Yes, it makes sense.
Okay, good. So now that I have that, I can just plug in my numbers and solve for Kc. Kc would equal NH3 concentration is 0.278 molar times 0.355 molar, which then gives me 0.0987 molar as my Kc value. And with this, I can solve for Kp. So once again, the formula for Kp is Kc times RT to the power of delta N. In this case, delta N is equal to 2, because there's 1 plus 1, minus nothing, because there is nothing. So it's just 2. Does that make sense? Because we're ignoring the solid, it's 0 on the reactant side.
Yeah.
Yeah, okay, good. So now solving for Kp, let's plug in all our values. Kc is, as we've established, 0.0987 times R 0.08206 times the temperature Kelvin, which they gave us, 298 to the power of 2. And that gives us a Kp value of 59.02. Now, I didn't round it to the correct significant figures. I'm pretty sure I didn't round it to the correct significant figures, but me and Brooks both agree significant figures are stupid. And that should be your final answer. Now, for number 8, I actually don't exactly know how she wants us to solve this one. So for number 8, what you're supposed to do is to create a rice table and solve for your equilibrium concentrations as you normally would. But actually, hang on, wait a minute. Maybe I can solve this. Hang on. So question 8 follows the same formula. Everybody got all this down, right?
Yes.
Yeah.
Okay, cool. Let me erase it. So question 8, I couldn't solve it earlier, but I think I can solve it now. Says that at a specific Kc, we have a specific number, or we have a specific number for NH3 and H2S, or a specific concentration. So our concentration for NH3 is 0.166. And so is our concentration for H2S. Now, what we're trying to do is solve for their equilibrium concentrations. And since this is a reversible reaction, I am going to assume that those are going to be our initial amounts. Because if they are not our initial amounts and our initial amount is 0, instead, these would just be our final amounts, because it would just be 0 plus X. And they have to end at 0.166 molar. And our question would be done immediately. So I'm going to assume that's not actually correct, because what kind of teacher would make you do that little amount of work? Am I right? So filling out our rice table and assuming that these are our initial starting amounts, 0.166. And this one is going to be ignored again because it's a solid. We're going to add X. Get 0.166 plus X and 0.166 plus X. Does this make sense?
Yes, it does.
Okay, sweet. So now we plug it into KC. KC is just the concentration of NH3 times the concentration of H2S. And if we know those concentration, and we know that it's just going to be 0.166 plus X times 0.166 plus X. And they do give us KC. It's where is it? 8.5 times 10 to the negative third. We can just solve for X here. Solving for X gives us, plug it into my Mathway program. By the way, Mathway actually carrying my butt through all of calculus. Don't tell the calculus teacher I said that.
Are you just taking calculus and not stats?
Yeah, I'm just taking calculus. Didn't have room for stats. Decided to take my practicum in education and training class and teach K-level Chem instead, which great
Okay.
class, by the way. So I had 166 plus X times 0.66 plus X. So they're equal to 8.5 and to the negative third. Solving for X, I get, oh boy, two negative numbers. Oh boy, this is not great. Hang on. I think I plugged in something wrong. Give me 1 second. This is being a pain. I don't like this question because this question isn't clear as to how it wants us to solve it. And I wish he was.
X be negligibly too small, so the answer would just be 0.166.
Yes, in this case, it should. Because it is giving us negative values. I'm checking again to see if I did it wrong. But no, yeah, that explanation makes sense. We are going to assume X is negligible, making the solution what you started with. Sometimes you forget that's an option. Been a while since I've actually been in higher level Chem. But yeah, so that's that covered. Any questions as to 7 and 8?
Nope.
Nope.
Oh, okay, good. Let us move on. Now that 7 and 8 are done, actually getting through this faster than I expected. Let's go on to question 9. Question 9 gives you 3 scenarios and it wants you to solve for the equilibrium values or the equilibrium concentrations. And so if you don't know how to format this question correctly, it is done in 3 parts. So let's do part A first. In part A, or in all of them, it gives you a formula. A or becomes, sorry, or is in a reversible reaction. B, and the Kc is equal to 4.0. Now, something you should establish immediately is what the Kc formula is going to be. It's going to be the concentration of B to the power of lowercase b over the concentration of A to the power of lowercase a. Does that make sense? I just took this, plugged it into your regular Kc formula. Got it?
Yeah.
All right, good. So in scenario A, it is telling us that lowercase a is 1 and lowercase b 1. So our new formula is just going to be A. It is in a reversible reaction with B. So now we plug in our knowledge into a rice table. where A starts at 1.0, because it tells us that A always starts at 1.0 molar. B starts at 0 because it's a product. Subtracting on my reactant side, adding on my product side. Now I have 1.0 minus X, and then just X here. I can plug this information into this, which gives me a Kc formula of B on top, which is just X. There's no exponent, so I don't care about it. And then 1.0 minus X. I'm going to equal this to 4.0 because that's what Kc is, and then solve for X. This one is much more simple. Doing some basic algebra gives you an X of 0.8. Do y'all want me to work it out, or are we just good with continuing?
I think we're fine with continuing.
Okay, I shall continue then. So now we have all this information. Let us find our equilibrium values. The concentration of A here is going to be 1.0 minus X, which is 0.8, which gives you a 0.2. And the concentration of B is just the same as X, which is just 0.8. And these two are your final equilibrium values. Does that make sense?
Yeah, it makes sense.
All right. Now you do similar things for B and C. The only thing that changes is what the value of the lowercase a and lowercase b is. So let's run through that real fast. Depending on how fast I can erase this. Sometimes the eraser likes to act finicky.
Wait, where does it say that Kc equals 4.0? Oh wait, no, I see it. Never mind.
Yep, before all the AB parts. All right, and then this gets erased. And we're going to change it. And so now that we're doing part B, A is now 2, or lowercase a is now 2, and lowercase b is now 2. So our new formula is going to be 2a. It's an irreversible reaction with 2b. Filling in our rice table is a 0, is a 1.0, because it tells us it starts at 1.0. We're going to subtract 2x this time, because there's a 2 here. We're going to add 2x this time, because there's a 2 there. And then we are going to do 1.0 minus 2x, and simply 2x there. Plugging this into Kc. Oh, got something in chat. All right, Anthony. I will. This is going to be on YouTube, so you are going to miss questions 10 and 11, but they're not too bad. So plugging that into Kc, that gives me a Kc formula of putting b on top. That is going to be 2x. My brain is slowing down. 2x to the power of the coefficient, which is 2. Same thing for the bottom. We're just going to be 1.0 minus 2x times the coefficient, or to the power of the coefficient. Anybody confused on any numbers I have grabbed?
No.
All right, let's keep going. So setting this equal to 4.0, as the question has told us, will give us an x of 0.8. Oh wait, sorry, 0.4. Looking at the wrong question. Wait a minute, hold on. I just noticed a problem. My math is wrong on my notes. Let me actually work this one out then. So 2x squared becomes 4x squared divided by this value squared is, you know what, I'm just going to plug it into the program. Quadratics is difficult. A second. So the first part is, if y'all want to do this on your own, feel free to. Can y'all hear it whenever I'm moving around my computer?
Yep.
Yeah,
that
kind
makes
of,
sense.
but it doesn't really matter.
Okay. So it'll be all right. Solving for that gives me 1/3 and 1. I'm going to assume it is here. So we're going to assume x is 0.3 because it would be unreasonable to assume that at equilibrium, all of the reactant is consumed because 1 minus 1 would be 0. And that doesn't make sense because it's just equilibrium. So if x is 0.3, then I can solve for by equilibrium amounts. At equilibrium, concentration of A equal to 1.0 minus 0.3, which gives me, oh, sorry, yeah, 1.0 minus 0.3. I'll do 2 sig figs there, which should give me 0.67. And the concentration of B is just 2x. Oh, wait, no, sorry, bad math. Sorry. It should be 1.0 minus 2x. And that will give me 0.34. And the concentration of B is 2x, which gives me 0.66. And these are my final values. Does this make sense?
Yeah.
All right, let's move on to part C. In part C, sorry, this isn't like a smart board. I can't just like circle everything and then clear it. I have to like manually go through all of this stuff. Oops. Fix that up. All right, now for part C, we're looking at an A of 1 and a B of 2. So here, our reaction is going to be A. It's an irreversible reaction with 2B. Filling in our numbers, same deal. Only A is going to be minus x because there's only 1, and 2B is going to be minus 2x because there's 2. So this will be 1 minus x. Here will just be plus 2. Plus 2. 2x. Plugging this into KC gives me a KC of B is on top, 2x squared over A, 1 minus x. Set this equal to 4 and solve for x. See if I messed up on this one. Dang, it looks like I messed up on this one as well. ready for movement noises. Very hard to flip around this computer sometimes. So
What computer are you using?
it's a Dell Inspiron. It's a laptop. I can flip it into tablet mode, but sometimes the keyboard on tablet mode doesn't like to listen to me, so I have to flip it back over.
Ooh,
So that's all the
nice.
movement noises y'all are hearing. So here is going to be 2x squared divided by 1 minus x equal to 4. Solving for x. I'm going to assume it is the positive number. So here it is going to be 0.61. Whenever you do these, since it's in a quadratic formula and you plug it into a math program, it'll always give you two numbers. Just look for which one is reasonable. A good reasonable estimate is always going to be the number that doesn't eat up all of your reactant, or the number that isn't greater than your reactant. Because if it's greater than your reactant, it doesn't make sense, right? You can't have negative reactant. So here we have 0.61. Plugging this all back in to find our equilibrium amounts. We have a concentration of A being at 1 minus just 1x this time, which gives me 0.39. And the concentration of B is 2 times x, which gives us 1.22. Any confusion as to anything I've done? I know I've messed up on this part a bit, so it is reasonable to be slightly confused.
No, I think I get it.
All right. That is question 9 number done. Or number. I'm losing it. All right. That's question 9 done. Let's move on to question 10. Question 10 is asking for if the reaction initially contains 0.0500 molar of dinitrogen tetroxide, that's the element in the reactants, if you forgot how your naming works, what are the equilibrium concentrations of N2O4 and NO2? And what is the P at 500 Kelvin? So let's set up our reaction first. N2O4 in a reversible reaction with 2NO2. And it does give us the Kc. Does it? Where am I just looking ahead? Yeah, Kc at 0.5 or yeah, 0.513 Kelvin. And it does tell us the temperature. I don't know why I put a I don't know why I put a K there. I was probably just thinking in multiple places. But yeah. So let's set up our rice table as we always do. There's only 2 elements this time, or 2 compounds this time, so I'm only going to worry about 2. I'm going to assume my reactant starts at nothing, and my product starts at nothing, and my reactant is given to me to be 0.0500 molar. So for this reaction, looking at our coefficients, I'm only going to be subtracting 1x, and I'm going to be adding 2 x's here because of this coefficient right there. And our final equilibrium formulas are going to be 0.05. I'm not going to put in all the extra zeros because not necessary. And 2x. Now, next thing I need to set up is my Kc formula. What is Kc? Kc is products over reactants. I'm looking for the concentration of NO2 squared over the concentration of N2O4 with no coefficient because it's a 1. Now that I have that, I can plug these values in and set them equal to this Kc value up here. So doing that will give me 2x squared over 0.05 minus x is equal to 0.513. Finishing that up with all the mental math that you need for that will give me an x of, or sorry, not Kc. Will give me an x value of 0.0385. Anybody confused as to all these steps that we've been doing?
No.
Good. So the next step is to find our equilibrium values because that's what it's asking for. Our concentration for N2O4 is going to be this formula, 0.05 minus x, which is there, 0.0385, which equals 0.0115. If you don't want to do all that math. The concentration for NO2 is going to be 2 times x, which equals 0.0770. And these are your final equilibrium concentrations. Oh, that makes sense?
Yeah, it makes
Wait,
sense.
I plugged in that equation into MathWay, but I didn't get 0.0385.
Okay, let me plug it in again. I could have done something wrong. What did you get?
I got 2 decimals.
Which one are you assuming is your reasonable answer?
0.0428.
Okay, so let's see if I get the same thing now that I do it again. So.
Wait, never mind. I think it's because I didn't put the parentheses around the 2x squared.
Yeah, that sometimes does it. Here, let me check it again just to see if I messed up. Yeah, I'm getting the 0.0385. So now we know if you plug it into MathWay, make sure your parentheses are all in place. Is that your first time using MathWay?
Oh, I didn't know it had to be like precise like that.
Okay, okay.
Now I get it.
Yeah, no. So sometimes the advanced math programs are like that and they don't warn you. But now that we have our equilibrium values, we are now done with the first part of that question. The next part of that question asks us what the Kp is. So let's solve for Kp. Yeah, you give me a second. A lot of tiny lines to erase. So we know that Kc is 0.513, which means we can solve pretty quickly for the value of Kp. The only thing we need is delta n. What is delta n? sum of the coefficients of the products minus the sum of the coefficients of the reactants. In this case, it is 2 minus 1, which gives us 1. So looking at our KP formula again, which is just Kc times RT to the power of delta N. And I know that delta N is not 0, which means I have to do all the math. Doing all the math, or sorry, first plugging in my numbers gives me 0.5. That's an ugly 5. Let me redo that. 513 times R 0.08206 times temperature in Kelvin. They gave it to me in Kelvin. I'm just going to use it then to the power of delta N, which is 1. KP, plugging into our calculators, gives us gave me 21.05. And if she asks for units, it's in atmospheres. All good on this question? All good on this question. Oh, geez, my voice cracked.
Yeah, I think so.
All right. That is number 10 done. Now we are on to the last question. Number 11. Number 11 gives us a formula and says, which of the following will contribute to the production of CH4? So we have carbon, which is a solid, plus 2H2, which is a gas, is in a reversible reaction with CH4, which is also a gas. But they also give us something important, delta H. What is delta H? Delta H is the energy of heat, which is given or taken away based on this reaction. The number one thing you need to pay attention to when you're looking at delta H is this. Is it positive or is it negative? If it is positive, you're looking at an endothermic reaction. If it is negative, you're looking at an exothermic reaction. If the reaction is endothermic, that just means it is absorbing heat from the outside system. If it is exothermic, it is giving it away. You already know this though. This will become important later. So looking at this, let's look at scenario A. Scenario A says, and we're trying to make more CH4 here. If we do not make more CH4, we have failed somewhere. So looking at scenario A, adding more carbon to the reaction mixture. So we are adding carbon. By adding carbon, this will increase the amount of the reactants. And in response, it will need to make more product to balance it out based on Le Chatelier's principle. Everybody remember that? You know, if you change one side, the opposite side will increase to account for more of the other side appearing.
But since carbon is a solid, wouldn't it not matter? Because it doesn't really matter when it comes to the equilibrium equation.
Yes, but in this case, we're paying attention more to what would happen if we just added more into the system, right? In this case, you're trying to measure based on amounts, right? So if I have more of a specific substance, and even though in our normal math stuff, we would pay attention to it as a constant, here we're going to assume that there's a set amount and we're going to just add more of it. And also, if you add more solid carbon, that's more surface area. If you imagine it as like a giant cube of carbon surrounded by H2 molecules, that's more surface area for the H2 to come into contact with, which will increase the rate of reaction, which will increase the amount of CH4 that you're getting. Does that make sense?
Makes sense.
All right, cool. So that's our scenario A. Scenario B is just increasing H2. So here we are adding more H2. It follows the same logic as the carbon. You're just increasing the number of reactants, increasing the rate of reaction for the reactant side, which will give you more product. So both of these scenarios would create more of the CH4 stuff. The next scenario, scenario C, raising the temperature of the reaction mixture. So here's where this negative sign on the H comes into play. When I look at this, I see a negative sign. I know that negative means it's an exothermic reaction. It is giving away energy. And when it gives away energy, this energy becomes a product. Because it's giving it away, it's not absorbing it. When I add more heat, that is simply more heat for the system to give away. It's not gonna, it's gonna use it mainly to facilitate the production of, or it's, how do I say this? The system is already giving away heat. If you add more heat, it's not gonna produce more product because heat is a product. It instead is going to invest the energy that you're giving it to create more reactant. Does that make sense? Or have I confused people?
Yeah, you confused me.
Okay. Let me explain this in a better way. Say for instance, oh, that's not the eraser. Say for instance, I have a system. In the system, draw a box. That's my system. In my system, I have this cube. And this cube is reacting with a gas around it. That is causing heat to leave. It is an exothermic reaction. What happens if I add more heat? If I add more heat, there's more heat in the system, but the reaction itself is already giving it away. It's not going to use that heat to produce more of the reactant that or to produce more of the product that I want because it's giving away heat. So in this reaction, right, we're trying to produce this green product here. And when that green product forms, more heat is released continuously. More heat is released. So we know that in order to make that green stuff, heat has to leave. If I want that green stuff, I know that heat needs to leave the reaction. If I add heat, I'm not going to get more of that product because I know that that product only appears if heat leaves, not if heat enters. Does that make sense?
Yeah, that makes sense.
All right. So if we were to look at it in a different way, right? Say for instance, it was the opposite. Say for instance, this sign wasn't there, it was positive. Instead, what I would be looking at is an endothermic reaction. Here, it would be the energy on this side being added. And instead of heat leaving, heat would be entering the system. Right? It is now absorbing heat. And when it's absorbing heat in an endothermic reaction, it's using the heat energy to create more of the green product that I want. Which means that if I start adding more heat, that's more energy for it to steal and consume to make more of the product. So that's the difference between adding heat in an exothermic versus adding heat in an endothermic reaction. Does that make sense?
Okay, yeah, I get it now.
All right, sweet. So for our heat example, let's go back to what we were doing. The heat example. Here it was negative, which meant that heat was a product. Erase it on the other side. So in this case, since heat is a product, it is an exothermic reaction because it's negative, which means it's giving off heat. In order to make the thing that I want, which is the product, it's going to give away heat. So if I put heat into the system, nothing's going to happen except that more reactant is going to form. So C is not one of my choices. Now, part D, lowering the volume. A good way to think about this one is to think about it like, or is to just visualize it. If I have a big container and my reaction in it, once again, we're looking at the cube of carbon plus all the H2 gas around it. There's a lot of space for this gas to spread around. And the reaction only occurs if it comes into contact with the cube. So the more often it touches the cube, the more often this reaction will occur, which means more CH4 is going to happen. If I shrink the cube, leave the original cube the same size, that is a lower pressure. The lower pressure means that all the H2 gas is going to come into contact with the cube more often, right? There's less space for it to spread out and it's going to constantly bump into the cube, kind of like being in a spread out auditorium versus being in a very crowded hallway. So in this case, since I have increased the amount of time it's going to make contact with the cube, I am increasing the amount of CH4 that's being produced because they're constantly touching each other. So this is one of the scenarios that would give me more CH4. Does that make sense?
Yeah, that makes sense.
All right. Oh, oops. So now for our next one, adding a catalyst. In this case, adding a catalyst does nothing. Just remember that. Adding neon gas to the reaction mixture. So adding neon gas kind of does a similar thing to what we did with the volume. It increases the pressure within the system, right? So while you would think that, here, we'll draw two spaces of the same size. Imagine they're the same size, they're not drawn to scale. We have our carbon cube in the center. And we have all of our H2 gas here around it. Now, normally the H2 gas would occur at a certain rate, or the reaction would occur at a certain rate because it's only coming into contact with the cube. What ends up happening though is if I add a bunch of neon gas, that's more stuff that the H2 is coming into contact with, but neon doesn't react to anything. It's a noble gas, it doesn't react. However, if I add more stuff into a smaller space, that's like adding more people into a hallway, right? You're just making it more crowded. You're making all those molecules push against each other, making them bounce off each other more often. And in the process, making them bounce into the center cube more often. So while you would think that it actually stops the reaction from occurring as much, it instead causes it to occur more often because the reaction increases as you increase the pressure. Does that make sense?
Yeah, that makes sense.
All right. Well, that's everything. Any questions?
Nope. Are you gonna upload this to upload the recorded Zoom?
Yes, I'm going to upload this recording. I will have Katie send it over to you guys when she can.
Okay.
Outside of that, I think that's it. Any final questions y'all have for me, or is that all?
No, I think I'm good.
All right.
Yeah. Thank you.
Thank you, Marcus.
Thank
All right. Good luck with
you.
your test tomorrow. I will be
Thank
ending
you.
the meeting now.
All right.
Okay, bye.
All right,
Bye.
bye. Have fun.
Bye.